Now, of course, our motion isn't always just in one dimension, so we have to figure out how to solve these types of problems in 2 dimensions. So let's look at a skier on a 25-degree slope with a mass of 60 kilograms. What is her acceleration if friction is negligible? Well, gravity is pulling the skier towards the center of the earth. The ground is also pushing back up on the skier. Now, this is normal force acting in a direction perpendicular to the ground. After all, normal is another name for perpendicular. So if the surface is at an angle, then the normal force is going to be at an angle as well. What is important to note here is that the forces are not directly opposite with each other, so they cannot balance each other out. We actually end up with a net force. We can determine the direction of this net force by adding the gravity vector and the normal vector head to tail. This resultant vector shows us the direction and magnitude of the net force, and as a result, the acceleration. If you think about what motion the skier is undergoing, you probably guess that she was accelerating down the hill. From our problem, we know the mass is 60 kilograms and the angle of the slope is 25 degrees. We are looking for the acceleration of the skier. We have already drawn a free body diagram and determined the direction of the net force. Now it comes in handy to be able to rotate our coordinate system so that the x-axis follows along the direction of motion. Notice that the force of gravity does not act in any directions that we have defined in our coordinate system. It is acting at the angle to the direction of motion. This means we need to break it into its component parts. If we extend our coordinate system down to include our gravity vector, we can draw an x component for our gravity vector and a y component for our gravity vector. We call these FGX and FGY. The angle of the incline is the same as the angle between FG and FGY. Now, which one of those components is equal to the net force? Think about which of those forces is actually going to pull the skier down the slope. We can also look at what we ended up with when we added the gravity vector and the normal vector. The resultant of that ended up being the same as the x component of our gravity vector. So we can substitute FGX in for the net force in our Newton's second law equation. Now, how do we figure out the magnitude of FGX? Well, let's pull these vectors out so we can see them a little more clearly. And we can move our vectors so we form a right triangle. Now it's just a matter of applying our trig functions to determine our component. Our x component is opposite of the angle that we were given, so we will use the sine function to determine that component. We can plug this into our Newton's second law equation and solve for acceleration, since that is what we're trying to find. This looks great until you probably notice that we do not know what Fg is. Well, it's weight. And weight is the effect of gravitational acceleration on a mass. We can do that and substitute that into our acceleration term. So acceleration is equal to mg sine theta divided by m. Since mass is found in both the numerator and denominator, we cancel those terms and we're left with acceleration is equal to the force of gravity sine theta. So the acceleration of an object down a frictionless slope is equal to the acceleration due to gravity and the sine of the angle. So wait a minute here. Notice that it does not matter what the mass is. The acceleration down a frictionless slope is equal to gravity times the sine of the angle. And it is independent of the mass of the object. So whether you have a mouse accelerating down that slope or a truck accelerating down that slope, the acceleration will be the same. So let's plug in our variables. Notice that this acceleration is less than the acceleration due to gravity. This makes sense since our skier is not in free fall. So for our skier accelerating down a 25-degree slope, her acceleration is going to be 4.14 meters per second squared. And again, what if we have a ball accelerating down that slope? The acceleration will be 4.14 meters per second squared. What if we have an avalanche going down that slope? The acceleration will be 4.14 meters per second squared. We can reconcile this mathematical expression with the acceleration in terms of our free body diagrams as well. Looking at this diagram, we can pretty easily see that the net force is equal to 0. Since the object is on an incline of 0 degrees, we take the sine of 0 degrees, which is also 0, and put that into our equation to find that the acceleration is also equal to 0. What if our incline changes to 30 degrees? The sine of 30 degrees is 0.5. So plugging that into our equation gives us an acceleration of 4.9 meters per second squared. We can see that the net force is now larger than the net force when the object was on a level surface, and that the acceleration is in the direction of the net force. What if our incline changes to 60 degrees? The sine of 60 degrees is 0.866. Plugging that into our equation gives us an acceleration of 8.5 meters per second squared. Again, we see that the net force is now larger than the net force when the object was on a level surface or less of an incline. What if our object is in free fall? Well, there is no normal force now to work against the gravitational force. The angle of our incline can be defined as 90 degrees, and the sine of a 90-degree angle is 1. This gives us an acceleration of 9.8 meters per second squared. So you can see that the acceleration of an object increases as the angle of the incline increases. This acceleration can vary from anywhere between 0 meters per second squared to 9.8 meters per second squared. So think about that. Anywhere on Earth, the maximum acceleration that an object can have due to gravity is 9.8 meters per second squared. This probably coincides with what you already know about motion and inclines. If you've ever ridden a bike down a hill, or on a roller coaster, or on a sled, you know that the steeper the incline, the higher the acceleration.